Hi, in this video, contents related to fault-based anomaly detection will be shared. In UAVs, an anomaly refers to unexpected situation that deviate from normal operation parameters such as sensor data, motor performance, communication signals, or energy consumption. There are two types of troubleshooting approaches. The first is component-based troubleshooting, and the second is fault-based troubleshooting. The fault-based troubleshooting approach is a systematical method that starts with the most common and likely faults. Starting with the most frequently encountered issues often leads to quick solutions and saves times. By checking simple and common problems first, unnecessary, complex, and expensive solutions are avoided, ensuring cost efficiency. A systematic troubleshooting process is conducted using a fault database created from experiences. The fault-based anomaly detection approach provides a better learning environment for new technicians to learn and solve common problems in some UAVs. The UAV firmware identifies the anomaly or fault and provides suggestions for resolving the issue through application. It can also provide information about the source and type of the fault under a fault code. In this case, the solution is easier, and a quick resolution can be produced by referring to the fault codes section in the UAV's user manual. Common anomalies in UAVs include flight performance abnormalities, power system issues, communication interruptions, sensor errors, structural damage, and software or firmware problems. There are three main stages for early detection of these anomalies: pre-flight inspection, in-flight monitoring, and post-flight analysis. Before the flight, visual inspection, system diagnostics, and sensor calibration should be performed. During the flight, real-time telemetry data is analyzed, and onboard systems alerts are monitored. After the flight logs are reviewed, data is analyzed, and performance comparisons are made. Technicians and operators in drone operations should be aware of potential mechanical, electrical, and software failures that could endanger system performance and safety. Mechanical issues often manifest as various forms of vibration, motor failures, and structural damage that can significantly affect drone stability and flight characteristics. Electrical vulnerabilities, including power fluctuations, signal interference, and critical component failures, pose significant risk to operational reliability and mission success. Software and firmware failures lead to disruption that can cause potential control loop interruptions, navigation errors, and unpredictable drone behavior. Understanding these intertwined, complex failure categories requires comprehensive diagnostic skills, precision technical knowledge, and a proactive approach to maintenance and troubleshooting. An unstable hover condition can lead to various issues in UAV flight. In this case, there may be excessive oscillation in the status data and an inability to maintain altitude. Such a problem can be caused by several possible reasons. Firstly, incorrect priority settings can lead to such instabilities. Additionally, motor issues such as damaged or unbalanced propellers, worn bearings, or damaged windings, GPS signal interference or jamming, incorrect barometric sensor measurements, or being affected by airflows or center of gravity imbalance can also affect drone stability, causing instability during hover. As seen in this example, a signal anomaly can have multiple causes. In this case, it is necessary to start with the most common and likely possibilities and systematically progress to uncover the true case true cause of the event. Drifting in hover is characterized by the drone gradually moving from the designated position. This can also be observed as inconsistent position data in flight logs. Possible causes of drifting include GPS signal issues, compass interference, EMU calibration errors, unbalanced propellers, strong winds, and motor or ESC inconsistencies. These factors can affect the drone's positional accuracy and make it difficult to track the drone accurately. Unexpected altitude changes are the significant issues encountered in the drone flights. Such changes can manifest sudden increases or decreases in altitude data. Additionally, inconsistencies between GPS altitude and barometer readings can be observed. Several factors can cause this situation. Air pressure change due to thermal currents can lead to barometer errors. GPS altitude errors, flight controller firmware issues, barometer failure, or power system fluctuations affecting sensors can also cause altitude change. A decrease in UAV flight time compared to previous flight is another issue. UAV operators should notice when batteries drain quickly, resulting in shorter than expected flight times. They should also carefully examine the sharp voltage drop curve in the battery data. Possible reasons for this situation include aging or damaged batteries, increased power draw from motors or other systems, extreme temperature conditions, incorrect battery capacity settings, a malfunctioning charge or power control unit on the battery if present, and undiagnosed short circuits. Motor performance issue can create significant problems during the flights. Uneven RPM values between motors can be observed when reviewing flight logs. Additionally, unusual vibration or sounds may be noticed during the flight test. Possible causes of such issues include damaged motor windings or bearings, ESC failure, bent motor shaft, loose motor connections, or propeller imbalance or damage. These conditions can hinder the efficient operation of the drone, since such issues are critical to flight performance. They need to be resolved quickly. Signal loss or signal strength reducing is usually detected by drops in the received signal strength indicator data or telemetry gaps in flight logs, indicating missing information. Possible reasons for this situation include antenna damage on the drone controller, radio interference in the operating area, exceeding the radio control range, obstacle between the receiver and transmitter, reduced operating voltage in the transmitter or receiver, and faulty radio module. Controller latency is a significant issue in drone flights. During the detection phase, delays between control inputs and drone responses can be observed in flight logs. Additionally, slow controls are frequently reported in pilot reports. Possible reasons for this issue include signal interference, delays in the flight controller, and overloaded microprocessor due to unnecessary process, reduced operating voltage in the transmitter or receiver, servo motors or push rods rubbing against something, damage or low quality servo motors, and incorrect PID settings. These factors can negatively affect the drone's response speed and lead to performance issues. GPS inconsistencies manifest as high horizontal dilution of precision values, jumps or inconsistencies in GPS position data. Possible reasons for these issues include poor satellite coverage, electromagnetic interference, damaged GPS antenna, incorrect GPS module settings, and errors caused by reflective surfaces. These conditions can hinder the drone's accurate positioning and negatively impact the flight safety. Compass errors are an important issue to consider in the drone operations. During the detection phase, inconsistent heading data and failed compass calibration process are common problems. Possible causes of these errors include magnetic interference from drone parts or the environment additionally. Physical damage to the compass sensor, incorrect installation orientation, firmware issues, and extreme temperatures affecting sensor performance are significant factors. Identifying these causes and implementing solutions is crucial for ensuring the drone operates safely and effectively. Excessive vibration negatively affect UAV performance. Vibrations can be detected through several indicators. High frequency oscillation may be seen in accelerometer data and camera. Image may become blurry or distorted. Possible reasons for such vibrations include loose fasteners, damaged or unbalanced propellers, bent motor shafts, body damage or fatigue, and incorrect payload mounting. Asymmetric flight behavior is an important issue that UAV operators and technicians should pay attention to. Uneven veer or on landing gear and consistent tilting or drifting in one direction during hover can be observed. Loose parts on the drone may also be seen. Possible reasons for this situation include structural damage to body, misaligned motors or arms, uneven weight distribution, damaged propellers, and calibration errors in the flight control device. Unexpected mode changes are a significant issue for UAV technicians. Possible reasons include faulted firmware, incorrectly configured flight modes, and a malfunctioning mode selection switch. Additionally, electromagnetic interference affecting control signals and sensor errors triggering models can also lead to this situation. The UAV not flying properly after an update is another issue. If the UAV exhibits anomalies after recent software updates, this situation should be carefully examined. If flights show inconsistencies compared to previous experiences, possible reasons include hardware incompatibility or bugs in the new firmware version. Additionally, incorrectly performed update process or corrupted update files can also cause problems. Finally, incompatible parameters settings can be another reason for the irregular behaviors. Hardware diagnostics devices such as multimeters and oscilloscopes provide critical information about the electrical system. Vibration analyzers detect potential mechanical irregularities, and thermal imaging equipment identifies heat-related anomalies in drone parts. Complementing these physical tools, advanced diagnostic software provides detailed flight logs analysis, real-time parameter monitoring, and advanced debugging interfaces. Calibration tools, precision sensors, calibration tools, specialized motor test equipment, and comprehensive battery analysis device further enhance flight safety. Root cause analysis is critically important and allows professionals to trace issues back to their fundamental origins rather than addressing superficial symptoms. Technicians use decision trees and flowcharts to make more effective decisions in potential failure scenarios. Practical recommendations for anomaly detection include recording normal operating parameters for each drone and using these parameters as reference point. Comprehensive pre-flight and post-flight system diagnostics should be performed periodically. Regularly reviewing flight logs and conducting data analysis is also a critical step. If possible, automatic anomaly detection algorithms should be written or specified. Software developed for purpose should be used. Additionally, following known common issues related to your drone models on online sources such as DJI forums, Ardapilot, GitHub, and Reddit is beneficial. Keeping detailed records of all detected anomalies ensures better analysis of issues. In this section we covered fault-based anomaly detection. I hope the contents have been helpful. See you in the next content. Goodbye.